Welcome to a SCAR-sponsored event here at COP26 in Glasgow, Scotland. Today we're going to be talking about current trends and near-term changes in the Antarctic climate system, causes and impacts. I think we're going to explore what the future fate of the Antarctic ice sheet might be, and some new initiatives we'll describe that are going to try to reduce the uncertainty of Antarctic's future contributions to sea level rise. So I think we're going to begin with Tom Bracegirdle. Tom?
Thank you very much, Rob. And yes, so I'm going to start talking on a short talk focused on the climate aspects, the atmospheric variability and the ocean variability aspects of Antarctic climate change, and talk about the aspects that are relevant to ice sheet change. And then more details on that will follow later with later speakers. I'll be talking on behalf of one of the SCAR scientific research programs, AntClim Now. And so many colleagues have provided input towards this as well, so I should thank them for this. So just to start off with, a very simple picture. And this shows projections of future change in global mean surface temperature. But it also illustrates not just the slow or the background change in climate, but also the variability in the climate. So in the black curve, we can see the observed climate change. And it shows that for some periods it changes rapidly, and of other periods it's less rapid. And then the thin coloured lines show various different climate models. And each of these climate models exhibits a similar behaviour, but on average, they show a steady change under climate forcing. The different colours show different scenarios, so they show high emission scenarios and low emission scenarios. But as you can see, with each individual climate model, there's large wiggles along the way. So some of what I'll talk about today are the interplay between understanding these wiggles and their implication for future change, but also touch on longer term climate changes as well. So if we break down the prediction problem, looking into the future, into different phases, this picture here is quite a useful way of doing that. So if we think about the next year to decade, there are processes in the atmosphere and the ocean that will dominate how the climate or the weather conditions evolve. And then on longer time scales, external forcing such as greenhouse gases begin to dominate. Antarctica is a remarkable region of the planet in the sense that it shows very strong linkages to variability a long way away in the tropics. And this is particularly evident in parts of Antarctica that are very sensitive to external forcing, such as West Antarctica. And the map here shows the atmospheric connection between variability in the tropics and how it can be connected to regions such as West Antarctica. And if we look at West Antarctica and focus in on that region, this schematic here illustrates how wind variability near to glaciers in West Antarctica can impact on the inflow of relatively warm circumpolar deep water towards the ice shelves and ice sheets of West Antarctica. And stronger westerlies tend to lead to more warm water reaching the ice shelves and ice sheets. So a lot of the changes in Antarctica occur underwater, under the influence of atmosphere and ocean variability. And these changes, illustrated by this plot here, showing variability in the winds in the blue line, and then tropical variability in the other colored lines, show large multi-decadal variations in recent decades, from 1980 through to the present day, that are very strongly linked together. Warmer Pacific sea surface temperatures are linked to stronger westerlies and more changes or melting or thinning of the ice sheets and the glaciers around West Antarctica. So improved knowledge of these linkages from low to high latitudes is a major part of understanding how climate will evolve in the next decades to century. Another factor I'm going to talk about today are the westerly winds, the westerly wind system that blows right around the whole of Antarctica. This belt of westerlies is a major feature of the global climate system. Its strength and position vary significantly in response to climate change forcings. And this has already had major impacts on conditions around Antarctica. This example here from the Antarctic Peninsula shows how changes in the westerlies caused summer warming to the east of the Antarctic Peninsula in 2002, which was implicated in the breakup of the Larsen B ice shelf. And the westerlies themselves, you may ask, why are they changing and why have they changed? And the major factor in recent decades has been the hole in the ozone layer, or the ozone hole. Changes in stratospheric ozone amount above Antarctica strongly influence the surface westerlies. And depletion of stratospheric ozone leads to a strengthening and a poleward shift of these westerly winds, mainly in the summer season. We've been learning more about these changes in recent years, and a paper that came out last year by Banerjee et al. In 2020 showed, if you look at the top plot, how the ozone amount over Antarctica has declined up until about the year 2000, and then showing indications of stabilization and possible early recovery. And in the lower plot, it shows the position of the westerlies shifting poleward during the period of ozone depletion and then also stabilizing. And so the observations that we have are helping to reinforce our understanding of the linkage between the westerlies and this external forcing. A key question then is, how will the ozone hole evolve in the near term, and what's the implications for the westerlies and the Antarctic climate system? Our best estimates are, in fact, that the stratospheric ozone will recover gradually over the 21st century to near pre-ozone hole levels by the end of the century. But as you can see, we're just at the beginning of this phase, and so just still learning about how this may evolve. You may think then that if stratospheric ozone moves back towards where it was, that the westerlies may return to their pre-ozone hole conditions. However, over the 21st century, greenhouse gases and other factors will begin to become more important. And this is illustrated by these maps here, showing all forcings 21st century change in the surface winds around Antarctica. And they show the different seasons, so summer, autumn, winter, and spring. And these are changes following a high emission scenario and a mean of many different climate models. And you can see that even in summer, by the end of the 21st century, we in fact see increases in the westerlies rather than decreases as greenhouse gases start to dominate over the recovery of stratospheric ozone. This illustrates that the future, sorry, I should say I circled the West Antarctic region there. The point being that coastal Antarctica is at the edge of this poleward shift of the westerlies, so these changes have many implications for the sort of impacts that I've discussed earlier. Of course, there are other changes that have happened in recent decades and will happen in the future to other parts of the climate system. too many to explore in detail here. But one point I would also like to make is that global impacts and regional impacts extend also to the ecological systems. So climate impacts on Southern Ocean ecosystems are both regional and far-reaching, and involve biogeochemistry, biodiversity, and food security. So conservation management policies need to take account of these impacts and be responsive to change and enhance resilience. So that's just a point relating to other impacts of Antarctic change. So to summarize, current climate trends and variability are already having a significant impact on regions of Antarctica that are undergoing rapid ice sheet change. Longer-term projected future climate change is highly scenario-dependent, with greenhouse gas forcing dominating end-of-century change under medium to high emission scenarios. But if we keep emissions to lower levels, then the recovery of stratospheric ozone may lead to more of a recovery of the circulation and wind systems. Taking account of climate variability, looking ahead to future change, is important in terms of estimating the likelihood of passing specific thresholds, which is relevant to ice sheet change and other Antarctic impacts. And so I would like to end there, and hopefully that's given a sort of overview of some of the main large climate issues that will then be discussed in more details relating to ice sheets as the meeting goes on. Thank you very much.
Thank you, Tom. We'll turn now to Florence Colleoni, who is here from Trieste, and she will be talking about instabilities in the Antarctic ice sheet that could be triggered by the kinds of climate changes that we just heard about from Tom. Flo?
Yeah, and thank you, Rob, for the introductions. Thank you, Thomas, for introducing the Antarctic variability, atmospheric variability around Antarctica. And if you can put my slides on, which are not those ones, I could start perhaps. Oh, okay. Well, okay, sorry. So, here we will mostly focus on trying to bridging the past with the future and directly focusing on the Antarctic ice sheets. So an important aspect is to understand why Antarctica is vulnerable to climatic changes. And to understand that, it's important to understand its configuration. So geographically speaking, most of the Antarctic ice sheet is resting on a bedrock below the ice, okay, that is located above sea level, while part of Antarctica is also resting on a bedrock that is below sea level, okay, and those two aspects are really fundamental to understand the Antarctic ice sheet dynamics. And actually, most of the outlet glaciers that flows from the inland part of Antarctica ends up floating on the ocean, and all those floating parts are called ice shelves. And the dynamics that links the inland flow to the ice shelf is really critical, and everything that is at the boundary between the Antarctic ice sheets and the atmosphere and the ocean directly impacts what's going on from dynamical point of view, but also from sea level rise point of view. So, as such, the Antarctic ice sheet is subject to atmospheric warming, and all the atmospheric variability that Thomas has been describing is strongly impacting the surface mass balance. And this creates some melting on the floating ice shelf around Antarctica, which are at the lowest elevation points. And it's also subject to oceanic warming, which creates also some melting below the ice shelves. And we will see that this is one of the critical points of the projection of sea level rise. Actually, all the oceanic warming is at the origin of what we call ice sheet instabilities that can be further enhanced by atmospheric warming as well. So the first one is what we call the marine ice sheet instabilities, and actually it deals with the thinning of the ice shelf by melting from below because of warm water intrusions, and while thinning, they break up and the ice sheet step back, okay? So the critical grounding line, which is the last point that somehow touches the ground, just steps back very fast and it accelerates the ice discharge to the ocean. Another one that is directly linked to atmospheric warming is due to the fact that the meltwater on the top of the ice shelf penetrates into crevasses and creates some hydrofactoring that also disintegrates the ice shelf and causes the grounding line to step back. And these two instabilities have a timescale of a few centuries from the trigger to the consequence on the long term. And so we have a very fast trigger, which can be related to overshooting that Rob will detail further on. And that is related to the tipping point in oceanic warming and atmospheric warming, both in the past and in the future. And those fast triggers create those instabilities that have long-term consequences, and that causes multimeter sea level rise more than 4 meters, because most of the marine-based part of the Antarctic ice sheets are subject to this kind of instabilities. And just to illustrate those consequences, this is a part of what Rob's simulated at some point in the Amundsen Sea and illustrate those processes of instability. So you see that the trigger, until the trigger happened, the ice shelf there are not moving too much, but once the instability are triggered, it's really fast disintegration and also a huge disintegration. So it has really long-term consequences on sea level rise. So now most of those processes, we have been simulating them for future projections, but do we have real evidence of such instabilities? Because of those long-term happening, it's difficult to observe them really nowadays. And the answer is yes. If we go back to geological records, for example, we observed that for what happened during the last glaciation, when the ice sheet advanced at this largest extent position, while retreating, it deposited what we call frontal moraine at the grounding line, and by dating back the step during the retreat, we were able to date and the duration of such instabilities to about 2 to 5 centuries. Okay, so such instabilities, we recorded them in the geological records during the deglaciation in a CO2 context that is below 300 ppms. Okay, so this is far below what we are having today, because we are above 400 ppms in the atmosphere. And so it's just a warning to say that this can happen also with very low CO2 concentration, and thus a temperature that is just slightly larger than today, or almost equal to today. So that's a really critical aspect that paleo record can tell us. But now if we go back even further in time, you can see that if we want to understand our future projections in the context of the Earth's climate history, we only reach similar projected concentration if we go back at least 3 million years in the past, okay, where sea level was higher by at least 10 to 20 meters, which implies that most of the West Antarctic ice sheets and part of the East Antarctic ice sheet collapsed at that moment, okay? And we were about, with concentration of about 400 ppm, a bit above, so we are just there. The tipping point is not really far away. So the thing that is, because those instability have very long-term consequences, it takes generations to reverse the effects of disintegration of ice shelf and discharge into the ocean of a lot of mass, actually. So we have a moral responsibility to really understand that those instabilities can be triggered if we do not put too much into efforts to make actions to adapt and mitigate our emission. But to understand that, we need also to bridge the paleo record with the present day observations and our future projection. And actually, this was a call for a broader community to merge somehow, and this was the birth of a new SCAR program that is called INSTANCE, which main focus is about studying this instability and threshold in Antarctica. This really represents an unprecedented multidisciplinary community effort, because all the aspects at the interface between the ice sheet, the atmosphere, the ocean, and the bed below will be definitely focused on and investigated, discussed. And the main point is that we really want to try to bridge together present-day observation with paleo reconstructions to really identify what are the key rate determining processes, and try to improve the model physics, which now are a bit stuck in the physics, really. What we hope to do with such a program is to reduce the uncertainties on sea level projections, and in particular to understand the fate of the low confidence SSP 8.5 scenarios that now in the IPCC report actually is this dashed line, which is the only scenarios that account for ice sheet instability in the simulations. Okay, it has only been done with a few models actually, while all the other scenarios that you see on this curve of sea level rise actually have been done with models that do not account for those ice sheet instabilities. So because we know that paleo records really have seen that this happen, we know that such scenarios can be very likely to happen as well. So we still need to understand what are the atmospheric and oceanic processes linked with those instabilities, and there are still big uncertainties about them, because it's really challenging to retrieve observations and understand the processes at the interface, and especially below the sea level actually in the ocean. And we also want to enhance the importance of paleoclimate records for unconstrained processes, which are most of this instability actually. And that's an important point. So what will be our future? We have big uncertainties in the emission pathways. We don't know what it will be actually. And so this gives birth to this large range of sea level rise scenarios. So we still have big uncertainty in the sea level commitment. But sea level rise is unavoidable. Okay, this is a physical fact due to the fact that ice sheet absorbs the heat and melts on very long time scale actually. Paleoclimate records clearly show that instability happens. So now we need really to focus to reduce uncertainties in the time frame for adaptation actions. And I will now stop here and pass to Rob that will detail more about projections and thresholds. Thank you very much.
Thank you, Flo. So this is a perfect segue. So we're going to now look at the implications of these instabilities that Flo just described and what they might mean for the future. And we will reflect on what a future might look like for the Antarctic ice sheet and the Antarctic system if we're able to stay within the sort of target temperatures that the Paris Agreement aspirations talked about, no warmer than plus 1.5 or 2 degrees warmer than pre-industrial. So this is another example of simulations of the Antarctic ice sheet. This is showing sea level contributed by a retreating ice sheet. And these are model results. And this model is attempting to include the instabilities that Flo just described. And you see that broad blue band. This represents hundreds of different versions of an ice sheet model, all with slightly different physics. So we would say that maybe anything within that range of blue is a feasible result. With these instabilities accounted for over the next 3 centuries, so you see on the bottom axis, we're looking at the next 300 years, we see a potential for Antarctica to contribute 10 or so, or perhaps even more meters of sea level rise to the global ocean. The little lines on the bottom that are much, much lower, you see a black line that's showing, maybe about 1.5 meters of sea level rise coming from Antarctica over the next 3 centuries. That's from the same ice sheet model that doesn't include some of these instabilities and processes. So what we're trying to do, what we're aiming to do, is to, understand where reality really lies. Is it those curves on the bottom, or is it something much, much more dramatic and serious for the world, like in the blue and the thick black line at the top? So this is an example of an attempt to do just that. So we're looking at the same set of simulations. Now we're focusing on just this century. This is an extreme, relatively extreme emission scenario, the so-called RCP 8.5. And if we look at the top left plot, it's the same sort of graph where we see a solid, thick red line. That would be our central estimate of sea level rise coming from Antarctica. And that is a set of model simulations that have no constraints. So we're playing with a range of physics in the model that are plausible. And now if we look to the bottom left plot, what we've done is we have eliminated the versions of the model that don't do a good job of simulating current changes in the ice sheet. And you can see that it's a little tough to see, but if you use your imagination, you can see that the band of blue is becoming a little bit more compressed. Now we do what Flo just recommended, is we think about some of these ancient geological records to help constrain the ice sheet model. That's the top right. And then the bottom right is even another set of ancient geological observations of what the ice sheet has done in the past. And you can see that we've begun to narrow that range of blue. We're reducing the uncertainty in these projections. And that's in part the aim of this instant program of SCARS. We can now take a model that has been calibrated based on observations and geological records and the behavior of the ice sheet that we see today. And we can see what happens to the ice sheet if we allow global warming to reach plus 1.5 degrees C. That's the top left plot. And what we're finding is that over the next century, the ice sheet really doesn't change much in terms of its response. It continues to contribute to sea level rise, but at a pace similar to today. The middle plot is a world that has been allowed to warm to 2 degrees, a little bit warmer than today. And we see a similar result, 9 centimeters of sea level rise coming from Antarctica over this century. But if we look at the bottom left, this is a world that we've allowed to warm to plus 3 degrees. And this is essentially where the nationally determined contributions put us if we were to follow current policy. And you can see that it's a very different picture. You see the red line, which is the pace or the rate of sea level rise, jumps dramatically toward the end of this century in a plus 3 degrees C warming. So we have crossed, we think, some sort of threshold in the system. And that threshold is just what Flo just talked about, where it's getting warm enough in the Antarctic system. The water under the ice shelves is becoming warmer, and even the atmosphere is getting warm enough in the summer so that we're getting meltwater on the surface of ice shelves. They break up, and big glaciers begin to retreat. What a plus 3 degrees C scenario for Antarctica might look like, this is one scenario from one of these model simulations. There's a nice, healthy ice sheet, the way that it looks like today. And if we look to the red box, that's the sector of Antarctica that Tom was talking about earlier, that is susceptible to warm air getting onto the flanks of the ice sheet and over ice shelves. We're going to keep an eye on that area where the red box is. And if we look to 100 years in the future, to the year 2100, we start to see some retreat. And the dramatic retreat is happening in 2 glaciers here, the Pine Island Glacier and the Thwaites Glacier that are labeled. And by 2100, in this scenario, the ice sheet has contributed 15 centimeters to global sea level rise. And we would add this to the sea level rise that would be coming from the Greenland ice sheet and from mountain glaciers, thermal expansion of the ocean. So this is a big additional contribution to sea level rise. But if we have a longer time scale perspective and we look a few centuries further into the future, this is what West Antarctica looks like. And again, it's because these instabilities that Flo described have kicked in, and we see 154 centimeters of sea level rise over the next 3 centuries, just coming from the Antarctic ice sheet, and mainly from West Antarctica and the Thwaites Glacier. Okay, is something like that stoppable once it begins? And so these will be experiments that we run with, in this case, with the same model, where we allow the world to follow an emissions trajectory following the NDCs, the nationally determined contributions, leading toward a world that's 3 degrees warmer than pre-industrial. And then the CO2 is rising in these line plots, graphs of different colors that you see on the screen. And then what we imagine is at some point in the future, we develop technologies where we're able to actually scrub CO2 out of the atmosphere. We're able to reduce atmospheric carbon dioxide. Those technologies have not been built to scale. They don't exist today, but this is just really a hypothetical exercise. Now, you see that the CO2 begins to return toward pre-industrial levels at different times in the future. So we're delaying the onset of when we turn on this CO2 removal. And we look to see how long we might be able to wait to start pulling CO2 out of the atmosphere before the ice sheet begins to sort of run away with itself, and the retreat, and the very fast retreat, becomes unstoppable. And what we have found is that, as shown in these line graphs on the top plot, is that if we were to basically maintain today's climate, the way the climate is literally now, in the year 2020 or so, the Antarctic ice sheet will continue to contribute to sea level rise, but again at a pace similar to the way that it is today. And that would be the black line at the bottom of the top left plot. And then we see a cluster of simulations where we have allowed the world to get a little bit warmer, and then we start to reduce carbon dioxide. And once we reach a point in the year somewhere between about 2060, what we find is that if we delay a reduction in carbon dioxide that doesn't begin to turn on until 2070, the red curve, you can see that there's a huge jump in the response to the ice sheet. So again, we have crossed some sort of a threshold where we've gotten to the point where the retreat of the ice sheet and rapid retreat becomes irreversible, even if we return to a climate that is similar to pre-industrial. And if we look to the bottom left plot, those are the same sorts of simulations, only looking at a longer time scale, going out 500 years. And even though the world's climate is returning to pre-industrial temperatures, you don't see any of those lines begin to go down again. The Antarctic ice sheet continues to contribute to sea level rise. And you see that with every decade that we would delay in beginning to reduce carbon dioxide, there's a very long-term repercussion in the long-term response to the ice sheet. So delaying mitigation in the near term ends up having a huge effect on committed sea level rise in the long term. An alternative to developing technologies that don't exist today and reducing carbon dioxide, of course, is just not to allow the carbon dioxide to get into the atmosphere in the first place. And those technologies do exist. Okay, so to summarize, models of the Antarctic system that include the climate, the atmosphere, the oceans under and around the Antarctic ice sheet, looking to the future in a world that is allowed to warm to about 1.5 degrees warmer than pre-industrial. Over the next century, we see about 8 centimeters or so of sea level rise coming from the ice sheet, including, these are simulations that include these instabilities that Flo talked about. At +2 degrees, roughly the same result. The ice sheet continues to contribute to sea level rise at a pace similar to today. But if we begin to approach about 3 degrees Celsius, we have crossed a threshold where the ice sheet really begins to respond, and these instabilities begin to kick in, and they become more widespread in a number of important glaciers in Antarctica. If we have a very high emissions future, we see much higher sea level rise, 34 centimeters coming from Antarctica just within this century. But if we have a longer timescale perspective, that turns into more than 5 meters just in the year 2200. And if we have even a longer term perspective over 3 centuries, we could potentially be seeing something like 10 meters. Now, a question still exists: is this as fast as the ice sheet could potentially respond? Does this represent really a speed limit in these instabilities? We don't know. Something even more dramatic might be in store. And again, it will be one of the important roles of INSTANT to try to get at the bottom of that. Is this the worst that we might expect? Is this much higher sea level rise than is actually something that we're going to be facing in the future, or could we be facing something even worse? But at the end of the day, seeing a threshold somewhere between 2 and 3 degrees is, I think, very, very relevant for where we are here at the COP. To me, this is an important call for action, because the current NDCs just don't seem to be good enough. We need to aspire to do better and keep the world closer to no more than plus 1.5 or 2 degrees of warming. So I'm going to end there, and I'm excited to pass the baton over to Divya. And Divya, please feel free to introduce yourself and where you come from.
Hi, I'm Divya Navle, and I'm from India. And I don't know what I'm doing here, actually. I'm not a scientist, and I'm not an author for the IPCC report, but I'm here, actually, to answer the same question that I answered to myself 10 years ago when I was on an expedition to Antarctica, chosen as a young environmental champion. And the answer to that was because if someone like me who's not really studying Antarctica but is able to experience a place like that and understand our planet better, and really relate to what's happening in these reports to these places and ecosystems that are really important for the health of our planet. And if I'm able to take that story back and as a layman able to share that with people in the form of, a story that I have been able to put together, then I have made a difference. So with that, I want to thank each one of you here for the amazing work that you do. As scientists, you are the people who are able to really point us in the right direction to understanding what our planet is going through, and that climate change is something that we need to act on now. I also experienced, you can say, something that had happened in Antarctica even before I was born firsthand. So the ozone hole formed in the 1980s. But when I went to Antarctica, I actually experienced the ozone hole because I was on the ice one day and I forgot to wear my goggles, and my eyes went red. And, sometimes young people, we are, make mistakes, we forget things, and I paid a price for that, and I actually ended up with red eyes for 2 days. And that reminded me that, that nature is very powerful. And if we do not take care of it, then it has repercussions, it has consequences. So I think when Rob especially, you were talking about, a number of these projections of what could happen. So the ozone hole was formed before I was born, and I was able to experience it 20 to 30 years later. I've been twice to Antarctica now, and I've been able to experience it. And so similarly, future generations are going to experience it as well. And we don't know what that future will look like. People in the 80s did not know that ozone hole would actually have these kind of repercussions. With that perspective, I think what I'm trying to understand in many ways through my work with multiple think tanks who work in the Antarctic policy space is to look at what these futures mean, especially for young people. And coming from a country like India, I'm always wondering, with the largest youth population in the planet for the future, with the melting glaciers in the Himalayas and the sea level rise coming from both the Arctic and Antarctic melting, we have a number of issues that we need to be looking at, especially specific to sea level rise. And so I think it's something that we all need to especially for the audiences watching this live, it's really important for them to kind of make a connect that what we are looking at in the reports is because of actions that have taken place due to the Industrial Revolution over 100 years of time frame. But what we do today, even in the next 10 years, actually, as the IPCC report says, that we have a decade left. If we can act in the next 10 years, then we are still able to kind of overcome some of the tipping points that Flo and other scientists have been talking about. And to be able to then say that what we did through our actions and by holding world leaders responsible is to be able to bring us back from those kind of future disasters. So I think I want to be able to leave here learning as much science as possible at COP26, and to be able to take this back and take the message of the scientists as well as what the world leaders do to really convert it into concrete individual actions back home. And that Antarctica is a global common after all, and it belongs to each one of us. So it's really something that we need to take care of.
Thank you, Divya.
Okay.
Well said.
Thank you.
Fantastic.
Can I pass it on?
Please do.
Thank you.
Yuri?
Yeah, thank you. My name is Yuri Rogel. I was a coordinating lead author on the IPCC 1.5 degree special report, particularly looking at pathways limiting warming to 1.5 degrees. And after the different pieces of information that you heard of the other panelists, including how critical tipping points or tipping elements of the Antarctic ice sheets could be triggered at warming beyond 1.5 or 2 degrees, I think it's particularly interesting to see how those extremely detrimental outcomes could be avoided. And fortunately, the IPCC prepared a report on this just 3 years ago in 2018, and I want to draw on some of the insights of what it would take to limit warming to 1.5. So let's start with global emissions. Over the past century, global greenhouse gas emissions have been increasing. Now, to limit warming to 1.5, these emissions need to decline rapidly. Here, on the right-hand side of this slide, you can see emission pathways consistent with limiting warming to 1.5 degrees with no or limited overshoot. And you can see that despite there being many lines of global emissions that would limit warming to 1.5, they also all have some key similar characteristics. And the first here is that by 2030, that means over the next decade, all these pathways robustly decline their global carbon dioxide and total greenhouse gas emissions. For example, carbon dioxide in 2030 is in the range of 40 to 60%, or roughly a halving from 2010 levels. Now, these reductions, they don't stop in 2030. Even beyond 2030, they continue, and by 2050, these pathways reach roughly net zero carbon dioxide emissions globally. Now, if we add other greenhouse gases, including methane and nitrous oxide, then this net zero date is not reached by these pathways in 2050, but around 2 decades later. So these 1.5 degree compatible pathways reach global net zero greenhouse gas emissions around 2070. One important aspect to keep in mind here is that we also have an uncertainty in how much warming we will actually get or will be the result of these emissions pathways. They limit warming to 1.5 degrees with around a 50% probability. Even if we achieve those very steep and deep pathways that, and I will come back to that, represent a massive societal challenge, there is still a 1 in 10 chance that warming will actually end up above 2 degrees. So even under these pathways, it is extremely important to understand the risks that remain and that society will have to deal with. And as was shown in previous presentations, in many cases, no matter how deeply we reduce our emissions, we can limit the impacts that are projected, but we can't fully eliminate them. Now, how do we achieve these extremely deep greenhouse gas emissions? The IPCC came forward. I don't have time to dig into every single technical detail here, but I want to give you a general idea of what is required here. And the IPCC highlighted that to hold warming within 1.5 degrees, we need rapid, far-reaching changes on an unprecedented scale. And each of the words in bold here actually has specific meaning and has specific evidence underpinning the choice of that word. Rapid, as you could see in the previous slide, means that we need to see global emission reductions, steep emission reductions within the next decade. And the simple reason for that is that if we don't reduce our emissions by 2030, we will have emitted the carbon budget that is compatible with limiting warming to 1.5, and that window will have closed by 2030. And that is why also COP26 and the discussions here are important to mobilize action over the next decade from this year onward. The next word in bold is far-reaching. And far-reaching here refers to action, that action is needed in all sectors. It's needed, or we need to change the way in which we produce our energy, in which we use our lands to grow the food or the fiber that we use as a society. We need to rethink how we move around, how we build our cities, how we design our houses. And finally, in the industrial sector, we really need to reconsider how many products we use and how we produce those products. And finally, on an unprecedented scale, refers to the fact that nobody is off the hook. Action needs to happen in all countries and across all stakeholders, from the large multinationals, from the large oil and fossil fuel companies, down to the poor and vulnerable communities that also need to be taken along in this global transformation. Nobody can be left behind because of the scale that is required globally of this transformation. If we don't manage for this to be an inclusive transformation, our evidence tells us that it will most likely be not feasible. Now, what has been progress to date? Here I draw from a report that was published last week by the UN Environment Programme. It is an annual report which is called the Emissions Gap Report, and it looks at where emissions are heading and where they should be going. And here on the left-hand side you can see an overview of global greenhouse gas emissions. At the bottom you can see 3 colored ranges in yellow, green and bluish colors that of where emissions would be going for 1.5, 1.8 or 2 degrees. At the top of the slide you can see where emissions would have been going if we would have no further policies beyond 2010. But then also in the second scenario from the top, where current policies are leading in terms of emissions. Now, current policies, as was already indicated earlier, still lead to strongly increasing temperatures, and under projected current policies until the end of the century, there is still a 1 in 4 chance that we end up with warming above 3 degrees, for which previous presentations have shown there massive changes in the Antarctic ice sheets are projected. You can also see here further shown that there thus is a big gap between where current policies or current pledges are leading us in terms of global emissions. Now the last question, now that we know what we need to do and what we are actually doing, the last question is whether these changes are actually feasible. And this was a question that was also asked to the 2018 special report of the IPCC. And the IPCC identified 6 dimensions or 6 tick boxes that need to be ticked for us to be able to say whether something is feasible. And some of these tick boxes, as scientists, we can tick without any problem. These include that whether we can limit warming to 1.5 or well below 2 degrees within the laws and physics of chemistry and physics that rule our world. Whether we can make that transformation within the carrying capacity of our planet. Whether we have the technologies or how much it costs. And all these boxes, we as scientists and as analysts or economists, we can confidently tick that this means that it is feasible to limit warming to the goals of the Paris Agreement. However, the 2 remaining boxes are boxes where we have to look into society. They ask the question whether society is willing to make the sometimes cultural and behavioral changes required to limit warming to those lower levels. And the second box is whether our political systems and our institutional systems are able to take the decisions and implement the policies that are required. And for these 2 boxes, we actually look into society, and particularly also today at COP26, to make the decisions required to make those deep emission reductions happen in reality. I don't know, who am I forwarding to?
Elizabeth Holland.
So we have a virtual presenter. I'm really happy to see Elizabeth Holland's face on the video monitor. And Beth, I'm not sure what you're going to present today, so please introduce yourself, where you come from, and we're looking forward to this.
Can't hear.
Can you hear me now?
Perfect.
Excellent. Well, and I'm so honored to be here as part of this virtual conference. I'm a lead author of 5 of the 6 IPCC reports, and the last, and I'll talk a little bit about the evolution with that. But I want to tell you about the transformation that I've been through as we went from the 4th assessment report to now the 6th assessment report. And let me see if I can get this up, please. So I am the professor of ocean and climate change and the director of the Pacific Center of the Environment and Sustainable Development at the University of the South Pacific. Between the 4th and the 5th assessment report, I had been so concerned about the science that I felt like it was really time to think about how to apply the science in communities. So I went from working with the Navajo Nation to working at the University of the South Pacific. And we serve 12 member countries in the Pacific, and many of them are listed in this map. And if we think back in time about what we're doing now, which is the United Nations Framework Convention on Climate Change, we have to remember that the original intention was preventing dangerous anthropogenic interference within the climate system. And what you've heard today is we're well beyond just the dangerous, and we're talking about significant repercussions. And the futures that we've heard about today are really concerning for us in the Pacific, because this is where we are right now. In the left-hand slide that you see here, we have the flooding, the now frequent flooding we have in Majuro in the Republic of the Marshall Islands. If you look in the top right-hand bit, you can see that there's an airstrip on this coral atoll in Tuvalu. The bottom right is the king tide bubbling up through that airstrip. And this picture was taken in 2009 and has become a much more frequent event today. So as we talk about, and as I think about as a scientist, how to translate what we're seeing in the projections, we can't always use these beautiful and stunning graphs that you've seen in many of the other panelists talk about. But we have to think about talking about it in another way, in a way that's more meaningful to those who in the Pacific. And so what I came up with is that a paddle, like you see here, paddling this va'a canoe on the sea, is about 1 meter long. So we can begin to talk about sea level rise as a meter. So when I came to the Pacific in 2012, I was able to bring a single paddle to a talk and convey to the community what we might be looking at by 2100. But as you've heard from Rob and the other speakers, that single paddle is no longer sufficient. So as we went from the AR5, I got my paddling team to help me with the left-hand bit to show what 3 meters of sea level rise might look like. After the special report on oceans and Cryosphere, which was released in September of 2019, right before before the COVID pandemic, we were talking about 5.4 meters of sea level rise, and that's 6 paddles. That's an entire va'a canoe worth of paddles. So, and I show them here just as we're trying to move through the water. But that's really what we're beginning to face. And what we heard from Rob just a few minutes ago is if we continue on the RCP 8.5, we're looking at 9.87 meters of sea level rise in the long term. And this is really an existential threat for those of us in the Pacific. But just to go back to this dangerous anthropogenic climate change and the impact on our communities and what's going on, since I arrived in the Pacific in 2012, we've had Tropical Cyclone Evan, we've had Tropical Cyclone Ian, we've had Tropical Cyclone Eta, which as a tropical storm in the Solomon Islands killed 25 people. We had record-setting Category 5 Tropical Cyclone Pam, record-setting Tropical Cyclone Winston, Tropical Cyclone Gita, which wiped out the capital city, the Parliament building in Nuku'alofa in Tonga. Tropical Cyclone Kenny, which hit the island of Kondavu hard. Tropical Cyclone Harold, which hit the Solomon Islands, Vanuatu, Fiji's Islands, and Tonga passed through in April following the outbreak of the COVID epidemic. So we were having to deal with both COVID and Category 5 tropical cyclone. Tropical Cyclone Yasa, another Category 5 tropical cyclone that passed through in December of 2020. And Tropical Cyclone Ana, which set rainfall record in January 31st of 2021. And so I just want to reflect back on what we in the Pacific has done. What you see here is is His Excellency Tony de Bruym walking into the Paris Agreement. And he started with the 5 principles that we're still working on. Increased ambition for 1.5 that we've seen even further evidence today. Legally binding. 5-year review with the upcoming global stocktake, loss and damage, increased access to finance. So as Prime Minister Bainimarama said in the presidency of the COP 23, we're really all in the same canoe. And that's one reason why I use this sort of thinking about how many paddles we're talking about. And that we really stand with the cryosphere community, and that we will not accept here in the Pacific any lack of resolve on the part of the community of nations in tackling the climate threat. And that was the statement of the Prime Minister in 2019 at the Pacific Island Forums meeting, the last time that we were able to convene in a face-to-face meeting. And because the ocean is so central to everything that we do in our ability to meet the Sustainable Development Goals, I just want to reiterate how important it is for us in the Pacific, in all 12 nations that I work for, and all 16 nations that I work with. And I'm currently a Nauru delegate and standing with the president of Nauru and the many Pacific leaders that have been calling for change. So Vinakabakalevu, thank you, Tomas, Komaltata. I really appreciate the honor of being able to participate in this event.
Thank you, Beth. That was powerful. So I think we're going to open the floor up to questions now, and we'll be looking for questions from our virtual participants and folks who are streaming. So we have a question for Tom. Tom, how much is Antarctica warming now?
That's a very good question. And Antarctica is a very large continent, so there are many different regions, and they're all warming at different rates. So we've seen quite large warming over the Antarctic Peninsula, and we've seen changes there of the order of 1 to 2 degrees centigrade or more. And other places where we see very little warming. That's partly due to the internal variability that I was talking about in the presentation before, where it takes a number of decades for the background climate change to emerge. So right now, there's some regions warming quickly, and some regions not warming so quickly. But of course, if you take any snapshot in time, there's going to be some warming and some cooling. And in fact, it's suggested that we could, places like the Antarctic Peninsula, could still see cooling phases of 20 or 30 years in duration, even later in the 21st century, with that background warming underlying change. So you can have the noise, as it were, on top of the signal can be quite large. So that's not a very definite answer, but that's because climate change at any one time isn't very clear. It's something that emerges over decades and centuries.
Yeah. Thanks, Tom. We have a question for Flo from social media. What are common triggers to cause tipping points?
Well, that's the big question, I would say. So we said before that we have ice streams, glaciers flowing to the ocean. So when we have the ice starting to float on the ocean, the floating part is exerting a back force to the inland flow that contains most of the inland flow inland, actually. And a trigger to such instabilities is when the ocean warms beyond a certain threshold that we are still to be determined, actually. The melting caused on the ice shelf actually make them too thin, and then the back force that they exert on the inland flow decreases, and this creates an imbalance actually in the ice motion, which triggers the disintegration, the calving of the ice shelf, and triggers the self-sustained instability somehow. So that's an interaction process with the ocean. It's not a process that occurs only within the ice sheet, actually. And when we talk about this, the other instability, that was the marine ice cliff instability, actually. So you have the same kind of process. Somehow the hydrofracturing is also decreasing the back stress that the ice shelf, the floating part, are exerting on the inland flow, and have the same effect as the marine ice sheet instability, actually. So that's that's really related to dynamics.
So it's the loss of ice shelves,
Yeah.
you're saying, is the key tipping point?
Exactly, I would say.
Great. We have a question from social media to Rob.
To yourself.
Which of the scenarios are most likely? 1.5, 2, or 3 degrees at present? That's really a question for Yuri, I would say.
Yeah, I'm happy. I'm happy to take it. I mean, in my presentation, I showed where emissions are heading today based on current policies. And in the emissions gap report, we assessed current policies to lead or to keep warming with 2 out of 3 chance below 2.7 by the end of the century. And so I indicated that there is still a 1 in 4 chance that we will actually exceed 3 degrees of warming if current pledges are being followed until the end of the century. Well, that involves lots of uncertainties and assumptions what happens after 2030. Most policies are short-term. And so there is a significant chance that if we just do what is currently on the books, we end up with warming well around 3 degrees by the end of the century, and still increasing thereafter, of course. However, when we look at what is being promised, what the ambitions are that are currently on the table, I think we are in a much more hopeful situation. If we look at the NDCs, so the pledges that countries have put forward for 2030, and we combine them with the different net zero targets that countries are also pledging for 2050 or 2060. Now India just yesterday with an ambition of reaching net zero by 2070, we see kind of medium projections of warming ending up around 2 degrees, maybe slightly below that. So that is in a much better place. The big caveat here is, of course, that ambitions and pledges are very important. They signal where countries would like to go, but what makes the world move is policies, plans, and actual emission reductions. And those need to be delivered now over the next couple of years, and parts of the discussions here at COP26 are also about providing financial support to developing countries to make those transitions and make those emissions cuts. So I think there is both a good reason to be still very concerned about where we are heading, and there is a good reason to be hopeful that there is a momentum and there is an ambition to limit warming to 2 degrees, if not to 1.5, if ambition can be further ratcheted up during this meeting and in the coming years.
Thanks, Yuri. So we should have some little bit more confidence in which path is most likely after this COP?
I think every year passing, we will have more confidence in where we're heading, of course. And each of those big climate summits are an important kind of milestone, an important meeting point to take stock, not in the formal way, but where global ambitions are, where the trust and solidarity between countries lies in terms of tackling this problem together. And that common understanding will ultimately result in whether we will ultimately determine whether we, as a global society, manage to limit warming to the goals of the Paris Agreement.
With regards to Antarctica, I mean, one thing we're finding is that an overshoot really isn't an option. It's not an option for Beth's Islands. You know, there will be disproportionate and unfair impacts if we have, you know, a lasting overshoot. No overshoot would be best.
Absolutely, and I think the cryosphere is of course one of the main systems with a long legacy and a long memory in terms of climate impact. And I think also there the ambition of the Paris Agreement is right. The ambition, the Paris Agreement actually doesn't allow for overshoot. The target is to hold warming well below 2 degrees, ever, always. So if we can do that while pursuing to limit it to 1.5, I think that is our first task today. I also think that once we have stabilized warming, given if we look outside over the past couple of years, I don't think a 1.5 or 1.6 or 1.7 degree world will be a desirable world. So we really at that stage, once we have made this first important step, we really need to think about how we are going to reverse this warming to lower levels. Not because we have aimed for overshoot, but de facto we will have ended up in a world that we don't necessarily want to stay in.
Yeah, it's a really important point. We have a question for Divya. What are the best options for young people to get involved in climate initiatives, both locally and globally? That's a great question.
Yeah, a great question indeed. And I'll start with where we are at right now. So the first thing young people need to do is get more climate education and awareness. So really listening to scientists, what scientists are saying, reading up reports, especially the IPCC reports. And I think there's a summary as well for policymakers, but also in general, I think the summaries of IPCC reports are very helpful. Young people can definitely, you know, not dig deep probably, you know, the reports are quite long, but looking at summaries is very helpful. But to be able to understand that the start of everything is through empowering yourself with education and knowledge. So after hearing what we have heard today here, I think even I would like to go back and learn more about the science in Antarctica as well to really see what is the impact that's happening, and then compare it to what the NDCs say. So I can look at my own country's NDC, and India set 2070 as their net zero target, but actually the Paris Agreement and other kind of metrics say that 2050 is when we need to really reach net zero. So we could hold our countries accountable in different ways, not only via social media, but also really going and talking to you know, policymakers about why certain targets have been set when the science is saying something different, and to be able to hold them accountable. So really empower ourselves with the science, and then go to the policymakers and ask the right questions, and be able to in fact, empower ourselves to be able to say that, yes, we would be able to convince policymakers to really uphold the targets of the Paris Agreement and reach a place where we are able to keep the temperature rise to well below 2 degrees Celsius and to limit to 1.5 degrees Celsius. Yeah.
Great answer. Okay, well, it looks like we're approaching the end of our time, and I want to thank all the panelists for some great talks, and to the folks who contributed some super questions. This was a lot of fun. And Beth, really great to see you. Okay, thanks.